now we're going to talk about absolute convergence, and then we're going to learn a couple of tests. One's called the ratio test and one's called the root test. So far, we've learned how to test the series for positive series, and then we've also learned we have a few tests for those, and then we've also learned one for alternating series. But what happens if you have a series that's got some positives and some negatives, but they're not necessarily alternating? They just pop up every now and then. How do you test a series like that? So we are going to learn how to do that. The absolute convergence is the first test we're going to look at. And it's just a definition. And so the definition for absolute convergence is that if you've got some series a sub n such that if you can show that if the absolute value of the terms of a sub n, the sum of the absolute value of these terms is convergent, then this series is called absolutely convergent, okay? Then that is absolutely convergent. That's its name by definition. And so the reason we care if it's absolutely convergent is because if it is, then we can say, therefore, the series is convergent. Then is convergent. Okay, so there's another definition on your sheet that says if the absolute value of the terms is not convergent, but the regular term is convergent, that's called conditional convergence. So that's just another term you can know. So here's the first example. It says determine if the given series is convergent or divergent. And so we have this, the sum of terms from n is 1 to infinity of the sine of n over n cubed. The sine of n over n cubed. Okay. So if we lay out a few of these terms, this would be the sine of 1 over 1 cubed plus the sine of 2 over 2 cubed, the sine of 3 over 3 cubed, and so on. And so if I put these in my calculator, I get something like 0.84 over 1 plus 0.91 over 8 plus 0.14 over 27, and then all of a sudden I get a negative term. This is not alternating, but it does have some negatives and positives in it. Minus 0.76 over 64 minus 0.96 over 125, and then some other terms. And so eventually this will turn positive, and then it will turn negative because it's a sine wave. And sine waves they're cycling every 2 pi. And so it's positive when it's in quadrant 1 and 2, and it's going to be negative when it's in quadrant 3 and 4. And so it's going to be flipping positive and negative, but not alternating. So what do you do with something like this? Well, if we can show that this series is absolutely convergent, then we can say it's convergent, and that's a test for convergence here. So let's just consider this. Let's consider the absolute value of these terms. I'll say, well, is this absolutely convergent? The sine of n over n cubed. Check the absolute value of that. Well, then all of a sudden this is a positive series, and we can apply positive series test to this. That's why this is helpful. So the biggest value of sine that we can ever get out of sine is 1. And the smallest value is -1, but the absolute value of 1 or -1 is 1. So the biggest value this could ever be is a 1. So we can compare this to this series right here. Let's see, the sum n is 1 to infinity. And this is a p series, and we recognize this, and this is a known series to us, where if p is greater than 1, then the series diverges. P is 3 right here, and it's greater than 1. So we can say this is a known series that diverges. This is known to converge, to converge. So I wonder what I just said, that was all wrong. If p is greater than 1, this series will converge, and so this is a known series that will converge. And so all of these terms are less than or equal to that. So by the comparison test, by comparison test, the absolute value of this series converges. So that means that by the comparison test, this converges. So what that means is this series, the sine of n over n cubed, is absolutely convergent. And therefore convergent. And therefore convergent. Okay, that's a T right there. Sorry about that. That's a convergent. Very good. Okay. So that's an example of how it works. So then we have some other tests we can use that are useful to use. The next one is the ratio test, and you see it on your sheet, but it basically says that you can take the limit as n goes to infinity, the a sub n plus 1 term divided by a sub n term, the absolute value of that ratio, and see what happens. So if you find that that limit is less than 1, it has a limit. First you find that it has a limit. If it has a limit that's less than 1, then we would say that the series converges. Or it's absolutely convergent and therefore converges. If you find that it has a limit that's greater than 1, or that the limit does not exist, then we say that that series is divergent. If the limit exists and it's equal to 1, the test is inconclusive and we can say nothing. We got to try something else to try to see if it's convergent or divergent. So that's kind of the rules for the ratio test. Any series could be applied. The ratio test could be applied to any series. So what we've got here, let's just write the rules basically. If you take the limit as n goes to infinity of the absolute value of the a sub n plus 1 over a sub n term. Okay, that's just how you do this. And we say this is less than, and it equals to L. If L is less than 1, converges. If L is greater than 1, or it doesn't exist, diverges. If L equals to 1, we do not know. Okay, we got to use something else. Okay, so let's see. When could we use something like this? Example 2. Determine if the given series is convergent or divergent. And so they give us this. N is 1 to infinity. We've got negative 1 to the n times n over 6 to the n. Now, this is an alternating series. However, it's kind of got some weird stuff in it. When you have like something to a power, 6 to a power, something like that, this is a good one to use in general when you have something like this. So let's try it and see what happens. This is a sub n right here. So if we take the limit as n goes to infinity of a sub n, the absolute value of a sub n plus 1, so this would be negative 1 to the n plus 1 times n plus 1 over 6 to the n plus 1 over negative 1 to the n times n over 6 to the n. This is what we have. Now, when we take the absolute value of that, what that effectively does is gets rid of this plus or minus. This is just 1 times something, which is just not changing the value, but changing it positive, negative. So we know it's already going to be positive, so that's like a 1. So that's what the absolute values effectively do. And so if you remove that, n is positive, so n plus 1 is going to be positive, and n is positive. And 6 to a power exponentials are positives. So I don't need these anymore. So I truly should have written this again. I said equals to without the absolute values. That's the best way to do it. But we're just going to proceed from here. So this is equal to the limit as n goes to infinity of n plus 1 over 6 to the n times 6 to the, n plus 1, 6 to the n over n. Yep. So what happens here, let's look at this. This is equal to the limit as n goes to infinity of n plus 1. 6 to the n plus 1 is basically 6 to the n times 6 to the 1. Because when you multiply like bases, the exponents add, times 6 to the n over n. All right, these can divide into each other. So basically, we're looking at the limit. This equals to the limit as n goes to infinity of n plus 1 over 6n, which is an infinity over infinity. So by L'Hopital's rule, this is equal to the limit as n goes to infinity of the derivative of the numerator, which is going to be 1 plus 0, or just a 1, over 6. And so this is 1 over 6. So the limit did exist. It's 1/6. 1/6 is less than 1. So we say that this series will converge absolutely, which means therefore it converges by the ratio test. By the ratio test. By the ratio test. Okay, that was example 2. All right, so now, let's see, we're going to do this again. What's my next one? Oh yeah, we have another little example. So let's see. Oh, this involves a factorial. So now I'm going to remind you what factorial means. Factorial is when you have a weird exclamation mark. Okay, that's what factorial the symbol is. And so basically, I'm sure you've seen factorials before, but it might have been a while. It might have been back in pre-calculus. We used that when we were using combinations, finding the coefficients for the binomial theorem is when I remember teaching them. So you might have seen them in that or in a statistics course or something like that. But if you haven't seen it, this is what it is. If we have something like 3 factorial, that means 3 exclamation mark. That means 3 times 2 times 1. That's what that means. If you have 7 factorial, that means 7 times 6 times 5 times 4 times 3 times 2 times 1. 0 factorial by definition is equal to 1, just so you know. So if we have n factorial, that means n times n minus 1 times n minus 2 times n minus 3 until we get down to 1. All right, so that's what a factorial means. So when you have a factorial, this is the ratio test is a good test to try. So let's look at this. Example 3, determine if the given series is convergent or divergent. We're going to sum the terms from 1 to infinity of 1 over n factorial. So let's see. Convergent or divergent? Let's have a look here. Example 3. Is this sum? Is that what it is? 1 over n factorial, is this convergent or divergent? So let's see here. Well, 1 over n, if it wasn't factorial, it was just 1 over n, we know that that is the harmonic series, and we know that that diverges. So, but I don't know about this, so let's do the ratio test. So let's take the limit as n goes to infinity of 1 over n plus 1 factorial, the a sub n plus 1 term over 1 over n factorial over a sub n. Okay, so the absolute value of this means it's going to turn everything positive. However, n is positive. 1 over something positive is positive. So this is equal to this. This is positive. Okay, so this is what we're looking at. So let's say this is equal to the limit as n goes to infinity of 1 over n plus 1 factorial times n factorial over 1. All right, so let's look at n plus 1 factorial. N plus 1 factorial over here, let's just say, what if we had 5 factorial? Remember, that's 5 times 4 times 3 times 2 times 1. Or we could say this is 5 times 4 factorial. We could write it like that. So we have n plus 1 factorial. This is going to be n plus 1 times n minus 1, and so on. So we could rewrite n factorial as n plus 1 times n factorial. This is what this is equal to. So I can write it like that. Well, if I write it like that, then it's easy to see these guys will cancel. So what I'm left with is 1 times 1 in the numerator over n plus 1 times 1. And as n goes to infinity, this is approaching 0. We did have a limit. It is less than 1. That means that this series is absolutely convergent, which means, therefore, it's convergent convergent by the ratio test. Okay, and now we're going to learn another little test called the root test, which is handy to use when you have something raised to an nth power. And so it's similar. In the root test says where you're going to take is the limit of the nth root of the absolute value of a sub n and see what happens. So it looks like this. The root tests go like this. Let me get this erased here. Oh my goodness, this takes forever. All right, so if we've got the root test, basically what we're going to do is we're going to take the limit as n goes to infinity of the nth root of the absolute value of a sub n and see what happens. And if we get a limit L, if L is less than 1, it converges. If the limit is greater than 1, or if it doesn't exist, like infinity, and then it diverges. If L equals to 1, then we can say nothing. It's inconclusive, similar to the ratio test. So what we're going to do here is look at example 4, which is a good one to apply this to. Determine if the given series is convergent or divergent. And so we're given the sum as n is equal to 2 to infinity of negative 1 to the n all over the natural log of n to the n. Okay, so this is an alternating series. It's true. But the alternating series test is not really going to get it for us because of this weird little denominator, the natural log of n to the n. So the root test is going to be a better one for us to try. So what this says is let's try it. Let's apply the root test. So let's take the limit as n goes to infinity. By the way, there's no conditions on which kind of series you can apply the root test to. So when you take the absolute value, it becomes a positive series, and we're allowed to apply it to any test. There's no preconditions on this. So we'll take the nth root of the absolute value of a sub n, of the absolute value of negative 1 to the n over the natural log of n to the n. Okay. When we take the absolute value again, that just kind of gets rid of this positive negativeness, right? So what this turns into is just a 1. So by the absolute value, if we take the absolute value, that turns into 1. For this one, I want to be a little more careful. This is equal to the limit as n goes to infinity of the nth root of the absolute value of this. When I take the absolute value, that's basically 1 over the natural log of n to infinity. And since this starts at 2, let's pay attention to this. If n started at 1, that would be a problem because natural log of 1 is 0, right? And if it started before 1, it'd be negative, but that's not a problem because it's starting at 2. So from 2 and beyond, the log's going to be positive. If you remember the graph of the natural log, this is a vertical asymptote right here. This is a intercept at 1, 0, and once it passes 1, it's positive. So it's over here at 2, so we're definitely positive forever. So we're fine. Okay. All right. So what's going to happen here? What did I put an infinity up there for? Oh my goodness, this is an n. Okay. What I could do is if I want to think of this as like 1 to anything is 1, I can think of this as 1 to the n or 1 over the natural log of n to the n. That is the same thing. So the nth root of something to the n, these cancel each other out. So this is equal to the limit as n goes to infinity of 1 over the natural log of n. Well, as n increases without bounds, so does the natural log of n, and so this is going to 0. The limit is 0, which is less than 1. Since it exists and it's less than 1, we can say that this series is absolutely convergent or convergent by it converges by the root test. And so so that's how you can apply the ratio in the root test, and that's what absolute convergence is.